right. Let's start. So the plan for today is for you guys to help you with your assignment questions 5 to 8. If I have time, 8 I'm still developing, so it may not be complete by today's tute, but I will update it and post it on GitHub. Okay. So the first question is about properties of checking set, cardinality, member, subset, and power set of a set. This unless your assignment question asks you to use Mathematica, you don't need to. So these type of questions you can compute by hand and then submit your assignment. Okay, let me illustrate this by hand. First, okay, so the purpose of me writing this code here in Mathematica is sometimes you may get a very long list of sets, and then you may not be able to compute power sets. So you can use Mathematica to compute the power sets using subsets function and check the cardinality, that is how many elements in the set, using the length function, and check if a given set is a subset using subset Q function, and check if the elements belong to a given set using member Q function. Let me show you the working by hand. I need to switch to my iPad. Okay, in the question I've given you this set A here, and the first question I've asked is this true? Okay, so what does that mean? Okay, this symbol means number of elements. Okay. How many elements are there? Okay. And 2 to the power A means power set. Okay. Power set of A gives you all possible subsets. Okay. So for this case, for set A, how many possible subsets are there? That's the first thing you need to check. The number of subsets would be 2 to the power the number of elements, which is 3 equals 8. So you need to, your power set should contain 8 subsets, okay, of A. Okay, let's compute the power set of A. Okay, I'll say this is power set of A is, so 1 is a subset, 2 is a subset, the set 3 is also a subset, and 1 and 2 are subsets, 1 and the set, sorry, this is 3 are subsets, and 2 and set 3 are subsets. And the next one is we have completed the element sets with 1 and elements, sets with 2 elements, and set. The next one is sets with 3, which is the entire set. 1, 2, 3. And the last one is the empty set. Okay, so you can count. That's 1, 2, 3, 4, 5, 6, 7, 8. Okay, those are that's the power set of A. And this part says on the left-hand side, you need to compute the number of elements in your power set, which is 8. Okay. Is this equal to 2 to the power 8, 2 to the power 3, sorry. Okay. Which we have got is 8. So this statement is true, should give you true when you evaluate it. And the next question I've asked is the element, is this a subset of A? Is 3 a subset of A? Okay, what do you think? Can anyone guess? Okay, this should give you, because I don't see number 3 in A. That's false. The next one is the set 1, 2 an element of 2 to the power, which is the power set. Do we have it? 1, 2, yeah. So this should evaluate to true. Okay. Okay. In the next part I've asked is given another set B, 1, 2, 4, 5. What is A intersection B? A intersection B are common elements in both sets. So you've got 1, 2, 1, 2. The A intersection B should be equal to 1, 2. And A union B is everything in A and everything in B. So 1, 2 is in the set 3 and 4, 5. The next one I've asked is what is A complement intersection with B? If the space we are talking about is natural numbers, okay, and A complement is whatever which is not in A, and intersection with B is 4, 5. Okay, so that's 4, 5. Okay, you can check your answers using Mathematica if you want. Okay, and let me go back. Okay, in this part, I've described the set A is 1, 2, and the set 3. Let's check whether this is true. This part. Power set of A is computed using the subsets function. So I have previously defined an A. Let me clear. Okay, that's what we got when we computed this by hand. And then let's look at that's the length of the power set. That means like cardinality of the power set is the next part we got. 8. And this is just checking whether the left-hand side is equal to the right-hand side. Okay, that's true. All right. The next one is we want to check whether 3 is a subset of A. Okay, so this part is the second one, but I have also asked here, I have also checked whether the set 3 is in A as well. Okay. So the first part is true because we have the set 3 in A. Second part is false because we don't have 3 in set A. Okay. Okay, this part C is checking whether 1, 2 is an element of the power set. Okay, the set 1, 2 is an element of the power set. We can use the function member queue. Here I've concatenated this, like I've used the subsets to compute the power sets, and then checked whether 1, 2 is a subset. Okay. Okay, which matches with our hand calculation. Let me clear A. Okay, any questions so far? Okay. What is A? Kai, I have given what is A. A is this set here, 1, 2, and the set 3. Okay, I hope that explains. All right, second question. What do you mean? Did you mean you don't need to use Mathematica for question 7? No, unless your assignment question asks you to use Mathematica, you don't need Mathematica. I just used Mathematica here to show you that you can check your answers. There may be cases where sometimes you may have a very large set. Okay, so this is useful later on if you want to use this concept. Okay. Question 2, okay, is 2 sets. A is a set where K is a natural number. K is divisible by 2. Is K such that K plus 1 is divisible by 2. This part I'd like to show you by hand first, because although I have used codes here, table using table, these are really infinite sets. Okay, so I've used the code to check whether whatever we have done by hand is correct or not. If you did attend my 10 o'clock tutorial, I made an error previously here in my code, which I have corrected now. So please consider that. What's happening here? Okay, from your, from theory, you should know if k is divisible by 2, then k can be written as that for n, for some integer n. Okay, that's in general. And if k plus 1 is divisible by 2, k plus 1 can be written as that, which implies k is 2 and take 1. Okay. So then we have the set A is equal to, given like n is equal to, I take 1, 2, 3. This is just illustration. So the set A has elements 2 times 1, 2 times 2, 6, 8, 10, and it goes on. Set B has elements. If n is 1, 2 times 1, take 1, which is 1. 2 times 2, take 1, which is 3, 5, 7, 9, and it goes on. So what is A intersection B? Can anyone tell me? Empty set. Yes, good. Okay, A intersection B, there is nothing common, so we get empty set. And what is the set of A union B complement, okay, in natural numbers? So n equals, I'm guessing that's, and what is A union B? A union B is the whole natural numbers. Okay, and that means the complement of A union B, what is that? Again, I got empty set, okay? But this all depended on the values of n I chose, okay? All right. So I just wanted to illustrate this with this example, but consider another set C, where k is natural numbers. 0 is natural numbers. it depends on how your lecture notes are. Like some people define 0 in as counted numbers, that is natural numbers. Some people don't. I didn't. Okay, in many books, the natural numbers start from. Yeah, that's a good question. Usually natural numbers start from 1. It depends on the lecture notes. Okay. What does it mean? X is a natural number. I'm not too sure like how the course. Let me check. I need to check your like specifically what it says, but usually I didn't define natural numbers from including 0. Okay, but please do check your lecture notes. Okay, I didn't define here. I define natural numbers starting from 1. Okay. Yeah, n equals 0 plus in this case. Positive integers. And in the last part, before I go to the code, like I just wanted to illustrate how it goes. Okay, so define the set C as K is less than or equal to R for a given R. So if I say R is 10, okay, this is the set C, and I have like using the previous set A intersection R is 2, 4, 6, 8, 10, and then this says how many elements are there in A intersection C, which is 5 in this case. Okay, you can check this with a code. You can check this by simulation. Let me check. Okay, so this is a little bit code where I started before generalizing it with for any R. So I took R equals 10 and defined C depending on R. I use table function here because like A is infinite set, but I am not sure like you can represent infinite sets in Mathematica unless you use a special code. I am not aware of it. So I used table with this like with a specific number and computed the intersection of A and C, found the length, which is 5 in this case. Okay. And then putting it all together in a function which generalizes for any R. This is the function that I wrote. And the output, which gives is the same thing. Let me run through this. Okay. That's well. And so, and when this is 10, give me 5, okay, which we got previously. All right. Is there any question? Is this code clear to everyone? All right. Question 3. Question 3 is about estimating least square regression coefficients, which is a very useful, which is commonly used in statistical analysis, regression models. So if you're given data points, okay, A and Y, the first part is generate a million random entries in a given range for B0, B1, and estimate B, which minimizes the error. Okay. So how does this work? Does this really make sense? Okay. Let me explain what's going on here with these 3 data points. Suppose you have these 3 points as your data, okay? What the question is asking you to do is, let's say you plot these 3 points, X, Y, and let's say 1, 1, 1 is here, 2, 2 is somewhere here, and 3, 3, 2 is somewhere here, okay? And the question is asking you is, what is the best line, okay? Line of fit that passes through, that predicts these points, okay? So the line of best fit is given by B0, beta 0 plus beta 1 of your X values, okay? Now, we don't know yet what are these beta 0 and beta 1, so you are supposed to estimate B0, beta 0, beta 1 using Monte Carlo experiment, okay? Simulation, okay? So the idea is, let's say you generate 1,000,000 beta 0 and beta 1, and then you can represent your beta 1 and beta 0 as like lists or matrices. So that's your entries, columns. Okay, then there are like the dimension is maybe 1,000,000. Okay. Okay, that's the first step. Now take the next step is take each column, okay, and evaluate your line, like substitute your beta 0 and beta 1 into this line, okay, and get a y value, okay, get a y value. So yi equals beta 0 plus beta 1 xi, okay, and then check whether, okay, draw that line, check whether like whenever you draw the line, there will be some errors, okay, between the line and your data point, okay. So the aim is to minimize. So error is given by your observe your yi minus your beta 0 plus beta 1 xi. Okay, that's the error. Okay, the aim here is to minimize the error. To minimize the error, we use Euclidean norm, okay, which is the sum of squared of errors. Squared, I goes from your 1 to n, okay. So that's your target. So every time you took beta 0, beta 1, solve it, fit it into this equation, and then compute this sum of squared errors, okay? And then find out which one minimizes, like which beta 0 and beta 1 minimizes the sum, okay? Sum of squared errors. That's the target. So in your question, so in matrix form, this is given as beta 0 plus beta 1. X is 1, Y is 1, 2, 2, beta 0 plus beta 1 times 2, Y is 2, and 3, 2. This is given as beta 0 plus X is 3 now, so 3 times beta equals 2. So in matrix form, this part is given as 1, 1, 1, and your X values 1, 2, 3. That's B0, beta 1, beta 0, beta 1 equals 1, 2, 2. Okay, so this is really your matrix A. That's beta matrix. Then this is your Y. Okay. So in matrix form, this sum of square of error is given as A your beta minus Y, okay, the squared norm. All right, I hope that explains what you need to code. Okay, we are going to code this. Okay. Yeah, that's partial derivatives equal to 0. Okay. Yeah, the minimum is taken by taking partial derivatives equals to 0 and solving the equation. Yes. Okay. Let's try this. Okay, in order to develop the general method, I started coding first, even like computing beta using random real within the range 0, 5, and take two random real numbers, and the dimension is 3 here. Okay. So it gives me 2 by 3 matrix. Okay. And if you want to change, if you want to see this in matrix form, you can say matrix form. Okay. So we are going to use, every time we are going to use like a column from this matrix for our beta, and then evaluate the function and compute the no errors and compute the norm as well. Okay. Here, I just wanted to check whether I can take one of the columns. So if you have, okay, let me try this one. If you have 5 here, you have 2 by 5, and then it goes on like that. And here, I just wanted to say if you have 1, this is me just building the code. So I just wanted to check whether this is the first column. Yeah. Second column. And it goes on. Okay. Can you try this? Can you code this and compute the error? Yeah, there are built-in functions to do this. But I was just gonna, I am just trying to help you do your assignment. The other question is, okay, once we computed that, for the first column, I just wanted to compute the error and find the norm. couldn't evaluate why. Okay, now this is a list, so we can apply the norm function, compute the norm, which is 21. The errors are this one, the first one. You got 5 observed points, so you should get 5 errors. Those are the errors. And then sum of squares of the errors are given by the norm function. Okay. Is that clear? Oh, this is a vector of errors. Okay, or the list of errors I computed. Okay. Error is actually like a scalar quantity for each observed value. Yeah, yeah. Here I am computing the errors. Like for each one, you can compute the errors individually, but here I have computed them all. And let's put everything together in a function. Yeah, error and residuals are the same thing. All right. So just putting everything together in module function. I call this function line fit. You can give any name, and the local variable in the argument is number of runs, which I say is n. And the first part here, I have sample beta n times 0 within the range 0 to 5. And that is like 2 values. And the norm here is originally at first it's like constant values of zeros, which I will be filling in the code. And this for loop computes the error for each point and computes the norm and fill in the matrix here, the norm matrix. Okay. By the way, this star, like bracket star. Okay, this is something someone asked from me previously. So this bracket star okay, within this means is a comment. Okay. It's a comment and it's not going to be evaluated. All right. Then after computing the norms, I have found the minimum using the min function of that list. And if you want to if you want to see what is the minimum, you can print it. And the index here is asking which position of the norm matrix is the minimum. Okay? And I just wanted to see which position. You don't need actually to visualize it. And for that position, find which column of beta gives you the minimum. Okay. So all in one. And okay, let's run this twice. And increase it to 100. It's getting close to 0 point something. 0 0.4, 0 0.8. We should expect 0.5, 0 0.8. And you can increase the number of samples times you want to do this. Okay, I'm getting something close to beta 0 is 0 0.5, which is your intersection of the y-axis, and beta 1 is 0 0.8, which is the gradient. Okay. Now, this is just estimation using like simulation, but actually there is a formula which you can get used to compute the exact value of beta 0, beta 1, which is product of these matrices. A transpose times A take inverse times A transpose Y, which is a known fact. So using this formula, you should, if you get your estimate close to what is given in the formula, then your code should be good. So I got 0 0.5, which is close to what the estimate I got, and 0 0.8, which is close to the estimate which I got. All right. So far, so good. Okay, then the next part. Let's see. Next part is plotting your actual points and the line of best fit. For that, I've used list plot and plot. This part is like rearranging X and Y for the list plot. I tried the transpose, but it didn't work, so I used the thread function. Okay, this is the line because like it's almost horizontal because the estimate for the slope we got is 0.8. Oh, it should be 0.5. I need to run this. Oh, this is wrong. 2.5. 0.8. Okay. It's 3.4. Yeah, this list is all right. That's the raw data. Hmm. Something is not going right here when I showed both data and line because this line actually should be about 0.54. I'm not sure what happened, but I'll check this. Okay, and update the code. 0.9. It seems so. Okay, I think I'm running out of time. I will have a look at the code, this part once again, why it didn't show the line with the dots clearly. I was expecting the line to cut off the y-axis at 0.54. Anyways, the next question is about um, finding solutions of the equation, given equation. So I've started this and then I haven't completed the code, but I'll do this and update this on, post this on GitHub. The, the solution, like you can use, first of all, this binomial coefficient formula to compute how many solutions you should be getting. And then my idea of doing this is a recursive method. For example, if you fix x1 to be like 0 to 4, and then given x1, you could find the remaining terms recursively, okay? By solving this equation. I'll work on this. Have you got any question before I leave? I'll stop the recording.